Hello, I'm Paul Beckwith. I'm with the University of Ottawa Laboratory for Paleoclimatology. In this video, I'm going to talk about how climate change has made Hurricane Matthew literally a monster. Okay, so if you Google W underground, weather underground, one word, there's lots of information here on your local weather. And if you go down a bit, we have powerful Hurricane Matthew takes aim at Florida. So there's information on the forecasts, on the hurricane blogs, etc. Lots of stuff here. So I'm sure many of you have been tracking Matthew to see what's going on. So I won't go into those details. Lots of people have. What I'm going to do is I'm going to focus in this video on the climate parameters that have changed to make Matthew what it is. So climate change the biggest thing is climate change has increased the sea surface temperature and also the water temperature down deeper. So the hurricanes are becoming more powerful. James Hansen just came out with a paper on how for the last year we're tracking 1.3 degrees Celsius higher than the 1880 to 1920 mean. So for every degree rise, there's 7% more water vapor in the atmosphere. So 1.3 degree rise we're talking about 9% more water vapor in the atmosphere for starters. And that fuels these superstorms because as the water vapor convects upwards and rises, the water vapor condenses into little droplets on cloud condensation nuclei, and then these get larger, forming the precipitation. But when they condense, they release energy, which fuels it leads to more energy in the atmosphere and longer storms. So Matthew has set many records, including lowest latitude that a hurricane has formed in the Atlantic Basin. I think it's 13.3 degrees, which is about up here. You can't go lower than about 10 because there's land masses here. The previous record was a 13.7, I believe. And there's lots of other records being set because the water, as I'll show you, is extremely warm, much warmer than normal. So this is September 27th, and I can advance a day at a time here. So you can see this is going to be sort of the origins of Matthew. If I click ahead here, so here is where we see it. This is a day later. We see the tropical disturbance starting to form here. And I'll just advance a day at a time here. This is another day forward, so September 29th. And then the 30th. So you can see it becoming stronger. Doesn't move much to the October 1st. So this is just a few days ago. And then it ramps upwards, heads north. Here starts to curve. Remember that things that are moving in the northern hemisphere deflect to the right because of the Coriolis force. The Coriolis force is 0 at the equator, so you don't get storms forming within about plus or minus 10 degrees of the equator typically. And the Coriolis force is maximum as you reach the poles. Okay, so this is the second. And then of course it comes north and it hits both Haiti and Cuba, as we saw. And then heads right over to Florida, passing these other islands, including the Bahamas that was hit heavily. So here's where we are. I think that's okay, so here's the present situation. This is a projection moving forward. And, we can keep projecting forward. This is Nicole here, which turned into a hurricane recently. Will this thing let me go any further? I doubt it. Yeah, it does. Okay, so it's showing, the forecasted path of Matthew right along the coast, and then perhaps doing this loop and perhaps even coming back. Okay, so what conditions are causing this? Okay, so what we have here is, this is the sea surface temperature. So what you can see is, this is the sea surface temperature anomaly, actually. So the anomaly, if you take the 30-year mean of sea surface temperatures on this particular date, this is before the hurricane has passed through, before the tropical storm and system has passed through, then these are the temperatures in these. This is how much warmer the ocean is relative to the long-term norm. So varies 2.5 degrees there, all up here along the coast of Florida, it's over a degree. Okay, all up in this region, it's it's warmer than normal. Okay, so what we can do is, if we go here now, okay, so this is now the actual, so let's cut this so my computer's a bit faster. So this is the actual sea surface temperature. So you need 26.5 degrees or higher, and then the storms can extract energy from the seawater on the surface, and then if there's cold water below, that will, if the hurricane's not moving, that will quench the storm, so it has to keep moving to warm water. But if the sea surface temperature is warm, above the 26.5, and it's also warmer than that below, as the storm churns up the water, it's bringing not cold water up, but warm water, so the hurricane can travel more slowly and build lots of speed. So you can see the temperatures here. We're talking 31 degrees up in this region, and slightly less here and here, but still at least 3 degrees above that critical 26.5 degrees. So let's bring up the menu here and let's cycle through. So this is before the storm passed, so I'll advance a day so that you can't see much change in the sea surface temperature as the storm actually we're already at no additional data. We're already at October 7th, so this is October 2nd. So this is not updated every day, okay? So it jumped. So this is what it was on the 27th, and this is what it is here. So you would expect to see a decrease of the sea surface temperature as the storm is passing. But we don't really see that too much because the water, like I say, is warm to depth. Okay, this is the significant wave height and peak period just before the storm arrives. So let's cycle through. You can see the waves are building up here. So you can actually see, as the storm is moving through, the low pressure sucks up the water and causes a surge, but it also, the high winds create the intense waves. So we can see the progression of the storm by looking at the waves here. So we can see it moving up here and moving up here, and you can see Nicole over here. If you look at the waves up here, we're talking about 9-meter waves, all in this region, in this vast region. So what happens on the coastline is we've had sea level rise on the US East Coast, which has been quite rapid. Global sea levels are rising about 3.4 millimeters a year. The Gulf Stream seemed to slow down and go over the continental shelves more and raise the sea level along the East Coast in 2010, 2011. And in fact, instead of the 3.4 millimeters a year, we had a rise for a time there of 125 millimeters, but that was further north. But we're getting some subsidence of some of these deltas along the US East Coast. We're getting sea level rise from glacier melting, mostly in Greenland and Antarctica and mountain glaciers. Also, the Gulf Stream has been slowing, so the water is warmer in the Gulf Stream. Hot water, if this whole region of water is hot water expands, that causes more water to pile up on the coast. The storm surge, of course, is very large. when the low pressure from these low pressure storms, when the center is very low pressure, it sucks up the water, like I said, and if it happens on top of a high tide, plus with the wave action, it overruns lots of the shore. The jet streams are much slower and wavier in today's climate, causing an increase in frequency, severity, and duration of extreme weather events. There's more water vapor in the atmosphere, like I said, quite a significantly amount more, which is fueling these storms. So definitely under climate change, we would expect statistically to see more intense storms, not necessarily more storms. In fact, we've had a period of time since Sandy and even since after Katrina, where there's been not too many of these large storms affecting the U.S. coast. So if we look here at the ocean currents, then you can see this is the Gulf Stream. The currents are coming here, and then the Gulf Stream, the Gulf is very warm. You get these strong currents coming up the coast, which is the Gulf Stream, carrying a lot of heat over. So if the Gulf Stream is slowing down because of the cold blob south of Greenland, then, which has been a persistent feature in the last number of years, then the water tends to get piled up more on the east coast. So again, this is climate change that is changing the statistics of these storms via the higher water temperature. The water is staying warmer. It's warming up, of course, through the summer, northern hemisphere summer, and it's staying warmer for longer times into the fall. You'll recall that the minimum of sea ice ever was in 2012, around mid-September, September 15th, 2012 or so. And October 28th, 29th, Sandy was produced and came ashore in New York. Did that infamous left turn, which is extremely rare. Storms that come across the coast that are on that path normally will do a 270 and come onto the coast. But to turn left, there was atmospheric blocking from ridges and crests and things. So the jet streams are behaving differently. The ocean currents are behaving differently. Over 90% of the warming from climate change is going into the oceans to heat the oceans. And the oceans, once they're much hotter, are evaporating much more water and can build up these storms. Also, for a Category 5 in the Atlantic Basin this late in time, it's extremely rare. Formed this low at latitude is extremely rare. So what we have here is almost a worst-case situation with Hurricane Matthew, because it doesn't just come ashore and devastate one region as a Category 4 or 5. It comes right up the coast, and over the last 10 years, there's been so much infrastructure built, and people have been lazy because there haven't been too many storms, so there's been all kinds of infrastructure. So the only way this Matthew could be worse is if it was a Category 5 coming up the coast, and also if it hit the coast of Florida a bit further south and directly impacted Miami, because that would have been a worse case than what we have now. But apart from that, there's not much that could have been worse. So, in summary, we need to talk about the climate system, right? And the climate system has changed. This is just showing the jet stream behavior before the passage of the storm. So back, I think this was September 27th, before the thing formed. So if you zoom out here, you can see these incredibly crazy looping patterns. So these looping patterns are bringing up huge amounts of warm air high up into the Arctic, and the cold air is coming extremely far south. And patterns like this there's nothing normal about patterns like this. This is our new and weird climate, which is changing